Most gardeners are losing 40% of their soil moisture before noon. Not because they aren't watering enough, not because the soil is poor, because the wind is taking it, silently, constantly, every single morning. David Mercer is 61 years old. He lives in Tucson, Arizona, one of the driest growing regions in the United States. For 11 years, he ran a drip irrigation system that cost him over $380 to install and nearly $60 a month in water bills. His tomatoes were thin. His peppers barely set fruit. His soil cracked by July every year without fail. Then he tore the whole system out. He replaced it with bamboo stakes, twine, and dried brush. Total cost, $2. By the end of that first season, his tomato yield had tripled. His water usage dropped by 70%. His soil stayed moist 3 days longer after each watering, without a single drip line in the ground. What David built wasn't new. It was old, thousands of years old. At minute 8, I'll show you the exact measurements and materials to build this yourself this weekend. At minute 14, we'll cover why your current watering habit may actually be making your soil drier, not wetter. The ancient farmers of the Negev desert didn't fight the wind. They redirected it. The Bible does not romanticize wind, it documents it. Proverbs 25:23 states plainly, "The north wind brings rain." That is not poetry. That is agricultural observation. The Hebrew farmers knew which wind carried moisture and which one stripped it away. They built their gardens around that knowledge. Wind direction wasn't background information. It was a design input. Isaiah 27:8 goes further. It reads, "By driving her away, by exile, you contended with her. He removed her with his fierce breath in the day of the east wind." The east wind in ancient Israel was the kamsin, a hot, dry desert wind that could desiccate a field in hours. The text acknowledges its power directly, and the response described is not resistance. It is redirection. You drive it away. You deflect it. You work with the force rather than absorb it. This is the engineering principle buried inside the scripture. The ancient farmers of the Negev highlands understood this at a practical level. They built low stone walls, not to mark property lines, not for animal containment, but to interrupt airflow at ground level. These walls stood between 2 and 4 feet tall. They were staggered across hillside terraces, and they created what modern aerodynamics now calls a dead air zone, a band of still, protected air that sits close to the soil surface and dramatically slows evaporation. The mechanism is straightforward. When wind moves at speed across bare soil, it strips away the thin layer of humid air that naturally forms just above the ground. That layer is your crop's first line of moisture defense. Lose it, and the soil surface dries within hours. The roots compensate by pulling water upward faster. The deeper soil dries. The plant stresses. A 3-foot stone wall placed perpendicular to the prevailing wind protects a zone extending up to 30 feet downwind. That's 10 times the wall's height. The Negev farmers didn't need a formula. They observed the outcome over generations and built accordingly. But the formula confirms exactly what they built. Wind management was not incidental to their farming system. It was foundational. The scripture reflects that. When Proverbs names the north wind and Isaiah names the east wind specifically, these writers are describing real agricultural threats that required real physical responses. The $2 windbreak is not a folk remedy. It is a direct application of a design principle that runs through the oldest farming culture in recorded history. The USDA National Agroforestry Center published research showing that windbreaks reduce evaporation rates by 20 to 40% across a protected zone extending up to 10 times the height of the barrier. A 3-foot barrier protects 30 feet of crop row. A 4-foot barrier protects 40 feet. The math is direct. The protection is proportional. The University of Nebraska-Lincoln tracked crop yields inside and outside windbreak zones over multiple growing seasons. Crops grown inside protected zones yielded 10 to 25% more than identical crops grown in exposed conditions. Same soil, same seed, same water input. The only variable was wind exposure. Here is the physical mechanism behind those numbers. Wind moving at speed across a plant canopy creates a pressure differential. It thins the boundary layer. The thin film of still, moisture-saturated air that clings naturally to leaf surfaces and soil. When that layer is disrupted, transpiration accelerates. The plant pulls water from the root zone faster than the soil can recharge it. A consistent wind of just 15 miles per hour can increase a plant's water demand by 30% above what it needs on a calm day. The plant is not sick. It is simply losing water faster than the system can replace it. Reduce wind speed by 50% and evapotranspiration drops by 25 to 30%. That is not an estimate. That is measured aerodynamic response. The archaeology confirms the same principle at scale. The runoff farms of the Negev highlands, studied extensively by Israeli archaeologist Michael Evanari and documented by UNESCO, date back over 3,000 years. Evanari's team reconstructed several of these ancient farm systems in the 1950s and demonstrated they were fully functional. Wheat, barley, and fruit trees grown using only reconstructed ancient methods, no modern irrigation, produced consistent harvests in a region receiving less than 4 inches of rain per year. The windbreak walls were a core component of that system, not decorative, not incidental, structural. Wind is not a weather event to wait out. It is a measurable force with a measurable effect on soil moisture, and it has a measurable solution. Before you build anything, do these 2 tests first. Test 1. Go outside right now and tie a lightweight strip of fabric or a thin plastic bag to a stake at ground level. Watch it for 60 seconds. Note which direction it moves consistently. That is your prevailing wind direction. Do this once in the morning and once in the afternoon. Mark both directions on a rough sketch of your garden. Wind shifts between morning and afternoon in many regions. You need both readings before you place anything. Test 2. Water 2 identical sections of your garden bed equally. Cover one section with a single layer of burlap or cardboard weighted at the edges. Leave the other completely exposed. Come back in 24 hours. Press 2 fingers 1 inch into the soil of each section. The difference in moisture retention you feel is the difference wind exposure is costing you every single day. Now build the barrier. Materials: bamboo stakes or scrap wood cut to 3 to 4 feet tall, natural twine or wire, dried brush, straw bundles, or bundled palm fronds. Total material cost at most hardware stores or farm supply shops, under $2 if you source brush and stakes locally. Often free if you have yard trimmings. Placement: position your windbreak on the side of your garden that receives the strongest consistent wind, the direction your fabric test confirmed. Place the barrier at a distance equal to 2 to 3 times its own height from your nearest plant row. A 4-foot barrier sits 8 to 12 feet upwind of your crop edge. This prevents turbulence directly at the plant base while maximizing the protected zone downwind. Construction: drive stakes into the ground 18 inches deep, spaced 2 to 3 feet apart. Lash horizontal twine across the stakes at 12-inch intervals from ground level to the top. Weave or tie dried brush, straw, or bundled material through the twine rows. The barrier does not need to be solid. A 50% permeable barrier, meaning wind passes partially through rather than deflecting completely over, performs better than a solid wall. A solid wall creates turbulence on the downwind side. A permeable barrier slows wind gradually and holds the dead air zone stable. What to expect? Within 24 hours, you will notice cooler air temperature immediately downwind of the barrier, especially in the afternoon. Soil on the protected side will feel measurably more moist to the touch than exposed sections. Within 7 days, you will need to water the protected zone noticeably less frequently. Soil will hold moisture 2 to 3 times longer between watering cycles. Within 30 days, plant foliage on the protected side will show less afternoon wilt. Leaf edges will stay cleaner. Growth rate will visibly accelerate compared to any unprotected sections of the same garden. The barrier costs $2. The water savings begin within 1 week. The windbreak is the first layer. It is not the complete system. The ancient Negev farms operated on 3 simultaneous levels. Each layer addressed a different mechanism of moisture loss. Together, they created a self-reinforcing system that required almost no external water input once established. Here is how each tier works and how to build it. Tier 1, subsurface. The mechanism is capillary interruption. Moisture in soil moves upward through capillary action, the same physical process that pulls water up a paper towel. When the soil surface is hot and exposed, This upward movement accelerates and water evaporates directly out of the ground before any root can access it. The ancient farmers interrupted this process by placing a layer of broken pottery shards, gravel, or flat stones 4 to 6 inches below the soil surface directly beneath the root zone. This subsurface layer breaks the capillary column. Water rises to that layer and stops. It cannot continue upward to evaporate. It stays in the root zone where the plant can actually use it. Replicate this by digging a trench 6 inches deep along your planting row. Lay a 2-inch layer of coarse gravel, broken clay pot fragments, or small flat stones at the base. Backfill with your native soil. Plant directly above it. Timeline: effects begin immediately after installation. Within 7 days, soil in treated rows will stay measurably moist 2 to 3 inches deeper than untreated rows during the same conditions. Tier 2. Surface. The mechanism is evaporation suppression. A bare soil surface exposed to sun and wind loses moisture rapidly from the top 2 to 3 inches. That is the zone where most feeder roots operate. Lose moisture there, and the plant responds with stress before the deeper soil is even affected. Apply a 3 to 4 inch layer of organic mulch, straw, dried leaves, wood chips, or cut grass, directly on the soil surface around your plants. Keep it 2 inches clear of the plant stem to prevent rot contact. This layer reduces soil surface temperature by up to 20 degrees Fahrenheit on hot days. It physically blocks wind contact with bare soil, and it cuts surface evaporation by 50 to 70% depending on material density. Timeline: effective immediately upon application. No waiting period. The insulating effect begins the same hour you lay it down. Tier 3. Soil biology. The mechanism is biological water retention. This is the tier most modern gardeners never reach, and it is the most powerful of the three. When your windbreak barrier is built from organic material, dried brush, straw bundles, cut branches, it begins to decompose at the base where it contacts soil. That decomposition feeds fungal networks in the soil, specifically mycorrhizal fungi. These fungi form a dense web of filaments around plant roots that dramatically extend the root system's effective reach. A root system connected to a healthy mycorrhizal network can access water from a soil volume 40 to 60% larger than a root system without it. Additionally, organic matter worked into soil from decomposing mulch and barrier material increases the soil's water-holding capacity directly. Each 1% increase in soil organic matter allows that soil to hold an additional 20,000 gallons of water per acre. That is not a theoretical number. That is measured field data from USDA soil science research. You do not need to purchase mycorrhizal inoculant. You do not need compost teas or soil amendments. You need organic material on and in contact with your soil and time. Timeline: fungal network establishment takes 30 to 45 days under normal conditions. By the end of the first full growing season, the biological layer is self-sustaining. It improves each subsequent year without additional input. 3 tiers, 3 mechanisms. One integrated system that addresses moisture loss at the atmospheric level, the surface level, and the biological level simultaneously. This is what the Negev farmers built. This is what soil scientists are now reconstructing in university field trials and calling innovative. It is not innovative, it is ancient, and it works. The most common response to a drying garden is to water more. It feels logical, the soil is dry, add water. But in a high wind environment, increased watering without wind protection does not solve the problem. It deepens it. Here is what happens at the root level. When a garden is watered frequently at the surface, drip lines, sprinklers, hand watering, roots follow the moisture. They grow toward the water source. In a surface-watered system, that means roots concentrate in the top 3 to 6 inches of soil. They have no reason to go deeper because the water is always coming from above. This is called shallow root architecture, and it is a direct product of how modern irrigation is designed. A plant with roots in the top 3 to 6 inches of soil is entirely dependent on the next watering cycle. It has no access to the deeper moisture reserves that exist 12, 18, 24 inches down. When wind exposure increases evaporation from that shallow zone, the plant enters stress within hours. The gardener responds by watering again. The roots stay shallow. The dependency increases. The cycle repeats. Kansas State University Extension research documented this directly. Plants irrigated frequently at the surface in high wind conditions showed 35% higher heat stress markers than plants grown in wind-protected environments with less frequent deep watering. The heavily irrigated plants were not healthier. They were more fragile. The windbreak changes this dynamic completely. When surface evaporation slows, the gardener waters less frequently. The soil dries more gradually between cycles. Roots are forced to extend downward in search of moisture. Within one growing season, root depth in wind-protected beds commonly doubles compared to exposed beds receiving the same or greater water volume. A deeper root system is a more resilient plant. It draws from a larger soil volume. It buffers against heat. It survives dry gaps that would collapse a shallow-rooted crop entirely. Jeremiah 17:8 describes this plant directly. It reads, "He shall be like a tree planted by the water that spreads out its roots by the river and will not fear when heat comes. Its leaves will be green." This is not a promise extended to every plant. It is a description of a specific condition. Roots that go deep access consistent moisture, and as a result do not fear surface stress. The modern irrigation habit produces the opposite of that plant. It produces a shallow-rooted crop that fears every dry afternoon. The fix is not more water. It is less wind. Here are the actual numbers. A standard residential drip irrigation system for a medium garden bed costs between $150 and $400 to install. That does not include labor if you hire it out. Emitters clog and require replacement every 2 to 3 years. Tubing degrades under UV exposure and typically needs full replacement within 5 years. Average monthly water bill increase from running a drip system in a dry climate, $30 to $80 depending on zone and season. Add a shade cloth setup for wind and heat mitigation, $50 to $120 for basic coverage. Those also degrade under sun exposure and require replacement every 3 to 4 years. Over 10 years, a modern protected irrigation setup for a single medium garden costs between $2,800 and $5,200. That is a conservative estimate. It does not account for pump failures, pressure regulators, timers, or filter replacements. The biblical system costs $2. Bamboo stakes sourced locally or from a garden center, under $1 for a bundle sufficient for a 20-foot windbreak. Natural twine, $0.50 for the length needed. Dried brush, straw, or bundled yard material, free in most cases if you have any organic waste on your property. Total installed cost for a functional 20-foot windbreak with subsurface gravel layer and surface mulch, $2 to $8 depending on whether you purchase any materials at all. There is no motor. There is no tubing. There is no timer to program or battery to replace. There is nothing to clog, nothing to degrade under UV, and nothing to reinstall after 5 years. The organic components of the system, the brush barrier, the mulch layer, the subsurface organic matter, do not deteriorate into waste. They decompose into soil fertility. The system does not wear out. It improves. Each year, the organic material breaks down further, feeds the fungal network deeper, and increases the soil's water-holding capacity incrementally. A system that was worth $2 in year 1 is worth considerably more to your soil in year 5, because it has been actively building biological infrastructure the entire time. The modern system depreciates, the biblical system appreciates. That is not a philosophical statement. It is a description of two different relationships with organic chemistry and time. One system requires your money every year to keep functioning. The other requires 10 minutes of maintenance each season and pays you back in soil health compounding annually. Ecclesiastes 1:6 reads, "The wind blows south, then turns north. Round and round it goes, ever returning on its course." The wind is not a problem to solve. It is a constant to design around. It has always been there. It will always be there. The question is never how to stop it. The question is whether you have positioned your garden to work with its pattern or against it. The farmers who built the negative runoff systems understood this. They did not have drip emitters or pressure regulators or UV-resistant tubing. They had observation, stone, and time. They watched which direction the Khamsin came from. They built accordingly. They grew wheat and barley and fruit trees in a desert, receiving less than 4 inches of rain per year. And those systems outlasted every modern irrigation setup by approximately 2,900 years. Soil science is now catching up to what they already knew. The windbreak is not a primitive substitute for modern irrigation. It is a more complete solution. It addresses moisture loss at the source rather than compensating for it downstream. It builds the soil while it protects it. It requires almost nothing to maintain and continues improving without intervention. $2. Bamboo, twine, dried brush, 90 minutes on a Saturday morning. That is the entry point. Everything else the system does, it does on its own. If this approach is something you want to continue building on, subscribe so you don't miss the next video. We go deeper into ancient water harvesting systems that are being reconstructed by universities right now. Systems that predate modern agriculture by millennia and outperform it in dry conditions. Leave a comment below with your climate zone and soil type. It helps me tailor the next system breakdown to conditions that are actually relevant to where you grow. And if you know someone still paying $60 a month for a drip system that isn't performing, share this with them. The knowledge was never lost. It was just waiting to be picked back up.